Hi everyone, welcome to this video, and we're going to go over several questions in Laplace transform and the system response based on the frequency domain. So let's dive into question number one. We'll start this session with the calculation of the current um, and the voltage in a capacitor. So the question is asking that how the current leads the voltage by 90 degrees in a capacitor. So that's something that initiates the whole topic of calculation of the frequency domain analysis of capacitors and inductors and the way that they can be solved later on in a more complex method. So we know that the dominant relationship that relates the I of a capacitor to the voltage across the capacitor is C dV over dt, provided that the capacitor that we're dealing with has a capacitance of C, and the voltage across that is defined by Vc, and essentially the current passing through the capacitor is IC. We know that all of these are the time domain characteristics. However, we also need to know that if you convert them into the frequency domain using the Laplace transform, we have IC in terms of S equals C times the derivative is in time domain can be converted into multiplication of S times Vs in the frequency domain, and there is another factor of V0 that talks about the initial condition of the capacitor or the capacitance voltage at the very beginning of the calculation. If there is no initial condition, we can ignore this and consider that to be 0 as well. So you can easily figure out that this, in the simplest case, can be equal to CS Vs, considering the fact that V0 becomes 0. Now, IC has a factor of CS. When there is an S multiplication, we know that S is an imaginary number of j omega. So this multiplication of j adds a 90 degree of phase to the voltage in order to get the current value. So in a sense, if we are drawing the phasor diagram for the voltage, considering that the voltage is going to be in the horizontal axis, current then is going to be multiplied by a factor of j, which means that there will be a 90 degree of phase being added to the voltage. And in this case, this is going to be the IS. So this 90 degree is coming from the multiplication of j, which appears in the frequency domain. So that's how easily you can figure out that how capacitor voltage and current are going to be different from each other. In this case, the current is leading the voltage since the rotation is counterclockwise and the current is always ahead of the voltage. Simply in the capacitor, there needs to be a time required by the capacitor to fill up this tank with quite a bit of charge in order to get to a certain level of current. So that's why that current actually is leading. So essentially in a capacitor, the voltage needs some time to be accumulated inside this tank of a capacitor, and that's how the voltage stays behind the current. So that's why the current actually leads the voltage in a capacitor. It's the other way around in an inductor, by the way. So moving on, the second question is asking about expand the following expression into simpler terms. The reason of doing so is that when we end up with such an equation in terms of the output of a system or the output of a transfer function or a closed loop transfer function system, we need to convert it back to the time domain. And there are some tables that help us to convert the easy and simple frequency domain equations to time domain. However, this looks like a little bit more convoluted because it's multiplication of several terms in the denominator as well as numerator, and we need to actually convert it to a simpler form. That's why that we are using a method called partial fraction expansion, which deals with expanding these functions into simpler terms that they can be easily converted back to time domain. In this case, we are going to simplify this with a summation of several blocks with just one denominator. So if we consider a case that a denominator with only s inside it, and another denominator with only s plus 3, and another denominator with only s plus 6, are going to be summed up with each other, but with different coefficients that we don't know them yet. Now, our duty is to find these coefficients of a and b and c's, because as soon as we find them, then we can easily convert a over s into time domain, as well as b over s plus 3, as well as c over s plus 6. In order to find a, the way that we can do is to multiply both sides of this transfer function. I would like to call it as h. Both sides of h to s. S comes from actually the denominator of a. So if you multiply both sides of s, of h to s, then we can get rid of the denominator of a. In this case, then this becomes a plus b divided by s plus 3 plus c divided by s plus 6, but then they have s in their numerator as well. Now, if we calculate this at s equals 0, we can then remove the second and third terms, and then what will be left for s is only the first term, which is a. That is going to how a is going to be calculated. However, for this case, the right side of the equation becomes a, the left side of the equation comes from sh. So we need to multiply this by s, and in that case, you can see that how s gets canceled out in the denominator, and we will be left with only these 4 or 5 components. So I'm going to actually write them down here. 4 times s plus 5 times s plus 7 divided by s plus 3 times s plus 6. Now, if I substitute 0 instead of s, whatever I will get is 4 times 5 times 7 divided by 3 times 6, which we can then simplify that later. Now, in order to find b, by the way, we need to multiply both sides by the denominator of b, which in this case is going to be s over s plus 3. So let's multiply s plus 3 by h. And in that case, it would be a over s times s plus 3 plus b plus c over s plus 6 times s plus 3. Now, if we calculate that at the location of s equals minus 3, because this term actually now can be calculated at any value of s other than minus 6 and 0. So we are going to actually calculate at the root of this component, so that s becomes minus 3. In that case, these two terms go away, and we'll be left actually with only b on the right side of the equation. On the left side of the equation, by the way, we need to multiply s plus 3 by h. And in that case, if you multiply by that, this s plus 3 gets removed in the denominator, and it will be left by only this part. So I'm going to actually write it down here. 4 times s plus 5 times s plus 7 divided by s times s plus 6. Now it's going to be calculated with respect to s equals minus 3. So essentially it will be 4 times 5 minus 3, 2 times 4 divided by minus 3 times plus 3. So we can simplify that later. Similarly, c is going to be calculated with multiplying the denominator of c, which is going to be s plus 6, to both sides. So s plus 6 multiplied by h. On the right side, we'll be left with a times s plus 6 divided by s plus b over s plus 3 times s plus 6 plus c. And if we calculate this at s equals minus 6 this time, because minus 6 is the root of this denominator, then we'll be getting rid of these two terms, and we'll be left only with c. So let's calculate that at s equals minus 6. We'll be getting c. However, on the left side of the equation, we need to multiply h by s plus 6. We'll be getting rid of this component in the denominator, and what will be left is only this guy. So s plus 5, s plus 7 divided by s times s plus 3. Let's calculate that at minus 6. So if we do so, simplify it, it will be 4 times minus 1 times plus 1 divided by minus 6 times minus 3. So we can further simplify them. Now we could see easily that we can find a, b, and c as the simple numbers, and they're not going to be a factor of s. So these terms can be then easily converted back to time if you use proper tables. So this third question is asking find a covalent time domain function using the inverse Laplace. Over here, we're dealing with a second order function in the denominator, but it doesn't actually look like very similar to the ones that we could easily find an equivalent time domain with respect to the given tables of Laplace transforms. So in order to do that, we need to first simplify this in order to convert it to simpler forms. We have two conversions that I'm going to actually write them down here in terms of the time domain, that if the time domain function is going to be k e to the power of minus at sine omega t, it's going to be converted to k omega over s plus a to the power of 2 plus omega squared, and k e to the power of minus at, this time cos omega t. Then we have the conversion of k s plus a divided by s plus a squared plus omega squared. In order to make use of these ones, we need to have a second order function in the numerator that we already have. We just need to simplify them to find out what a and omega are, and then see which one of them actually we can make use of. So if we compare the denominator, we need to make a squared root from that. So simply we can write s plus 1 squared, but then what's missing over here is a constant number of 3 compared to this 4. So we can add a factor of plus 3 over there to equate that. In this case, we can easily see that 1 acts as if there's a, and omega squared is going to be 3. So our a is going to be 1, and omega squared is going to be 3, so omega is going to be square root of 3. In this case, let's also see that once we have got the denominators, our numerator could also be a factor of a constant value, or a summation of s is going to be turned up over there. Since we have a factor of s in the numerator, we have to make that similar to this first. So s plus 2 in the numerator now has to be s plus 1, because that's a, and then this could be also plus 1. So in this case, s plus 1 is going to act like s plus a, and this 1 is going to act like a constant number. However, it will not actually end up with a complete scenario because s plus 1 is shown here, but 1 is not shown as the numerator over here to make use of the second equation. So we need to actually further modify that. So we will get there in a sec. Let's try to actually create another equivalent function such that we would be using a constant value in the numerator, but then this should have a factor of omega, and omega in our case is going to be square root of 3. So our whole function is going to be, say, h, now can be split into two functions of s plus 1 divided by s plus 1 squared plus 3, such that I can say s plus 1 divided by s plus 1 squared divided plus 3 plus 1 divided by s plus 1 squared plus 3. So now if I want to correlate which one of these equations of a and b, let's call it this way, I can I can easily see that s plus 1 is generated as s plus a, and I can make use of b. So this part can be simplified with b. However, the second term has a numerator of 1, whereas we're looking for a numerator of omega at least. So in order to make that, we need to multiply that by the omega, which is going to be square root of 3, and then divide that by that in order to keep the same function. In that case only, we can make use of a conversion. So let's try to actually implement both of them. And in order to get that b, the time domain equivalent of part b is going to be k, which in this case is going to be 1, e to the power of minus 80, a is 1, and cos omega, which omega is going to be square root of 3t. However, part a is going to be k omega, which in this case omega is 1, a square root of 3, and k is 1. So we can easily write e to the minus of t sine square root of 3t. But then there is also a factor of 1 over square root of 3 that we need to consider that as well. So you can see that how easily these two functions could be converted into time domain and are correlated with each other. So that's how we can simplify complex functions with second order roots as well, even if they don't look pretty easy to be decomposed into single terms. However, the ht in the time domain can be composed of two sine and cos functions of the same frequency, but with different rates of variation. So let's dive into question number 4. This question, the first part of it is asking, find the transfer function of the following process control system. So in order to find the transfer function, we need to keep track of the feedback path first with respect to the output. We know that this node at the output is C, so whatever comes out of that is also C. So when C enters this block, it's going to be, imagine that we call it CH, and the output of that is going to be CH. Now, in this block that is error detection, R is going to be minus this input, which is CH, in order to generate the output of this block. So I'm going to write it as E, but we also know that E equals R minus CH. Then E is going to be multiplied by this K as well as this transfer function that we can easily call it G in the forward path to get to the output, which is C. So if A gets multiplied by K and then by G, then we get to C. Now I can easily write E in terms of C over kg and replace that here in the first equation to get rid of the e. So it would be r minus ch equals c divided by kg. If you solve for c, it would be r equals ch plus 1 over kg, which if I simplify that further, I get kg 1 plus kgh is going to be multiplied by c to get r. Now the total transfer function then becomes c over r. I can then simply write kg divided by 1 plus kgh. So that's the total transfer function that we were looking for. And now we can easily simplify that with just replacing k and g. So we can just write k. G is going to be 3 divided by 10s plus 1 divided by 1 plus, again, k times 3 divided by 10s plus 1 times 1 plus 4s plus 1, which if you simplify that in the denominator, we have 10s plus 1 times 4s plus 1, and we have 10s plus 1 in the numerator with a coefficient of 3k over there. Then in the denominator, again, we have this 1, which is going to be multiplied by this whole thing in the denominator and show up itself here. It would be 10s plus 1 divided times 4s plus 1 plus the multiplication of k times 3 times 1, which will be 3k. And now we can simply simplify these two terms. So it would be simply these two terms will go away, and these two terms will be multiplied together to make the new numerator. So it would be 3k times 4s plus 1. The denominator then becomes multiplication of 10. I'm going to actually simplify that now. 10s times 4s, 40s squared, plus we would have 10s and 4s would be 14s, then we would have 1 plus 3k. So that would be the total transfer function of the system of interest. So the second part of the question is asking, find the unit step response in time for k equals 0.075 in the previous system. So essentially, what we need to do is to replace k with this value. And I already have written the total transfer function of the system here. We just need to multiply them accordingly. So 40s squared plus 14s plus 1 plus 3 times k, and in this case, k is 75 divided by 1,000. If I want to actually simplify that to 25, it would be 3 over 40. So I'm going to actually write it down as 3 over 40 with the multiplication of uh, times 3. So 3 times k would be 9 over 40. And I can further simplify that into 49 divided by 40. So I'm going to actually replace that with 49 divided by 40. So again, numerator, it would be 9 divided by 40 times 4s plus 1. So now if you want to actually convert it back to the time domain, we need to use proper equations, but it might look a little bit difficult for us since this is the second order system, and there is not an easy way to decompose that. So let's try to find a way to decompose the second order system in the denominator. So 40s squared plus 14s plus 49 divided by 40. If I try to get to a factor that if I imagine that this would be my, let's call it b, for instance. If we somehow multiply b by a factor of 40, so if I move, there's a trick that instead of having that large coefficient at S2, you can multiply that to the final constant that we have and convert it into S2 plus 14S plus 49. And if we simplify that, we get to S plus 7 to the power of 2. So I'm going to actually write it 2 times S plus 7, S plus 7. Now that we had multiplied this 40 to the constant value, we need to consider that backwards, and in order to cancel out that extra multiplication. In order to do that, we need to multiply 40 first to this s, and also divide that in the second constant over there in order to cancel out their impact. So let's do that really quick. It would be then 40s, and also it would be divided by 40 over there. Now, if you do such a trick over there and simplify that, you get 40s squared plus 40s times this, it would be 7s, 7s, s times 7 is going to be again 7s, plus 7 times 7 over 40, it would be 49 divided by 40. So essentially, this is going to be exactly the same equation that we were looking for. So we could easily convert it back to multiplication of two simpler terms. In a sense, this is exactly the same as 40 divided by 40. So we moved the larger coefficient and multiplied that to the constant number, and then simplified that, and then tried to cancel out its impact by one time multiplying at the s and one time dividing that by the other constant or the other root. So let's just simplify the original c over r. That is going to be 9 over 40 times 4s plus 1 divided by 40s plus 7 times s plus 7 over 40. If you take a closer look at this equation in the denominator, we can see that both roots are exactly the same, even if they are distributed slightly differently. But the root over here is minus 7 over 40, and the root over here is also going to be minus 7 over 40. So we're essentially can write it down as s plus 7 over 40 to the power of 2. And in order to do that, we need to actually factor out 40 from the first term. Now we can also simplify that here, 4s plus 1. Now that we have the second order function in the denominator, we can simplify that better with respect to the functions that we have, the conversion equations that we have in terms of time domain and frequency domain. The way that it really works is that we need to simplify that to either a case where there would be k over s plus a squared, which in this case is going to be converted into kt to the power of minus at. So that is the time domain equivalent of this case, but this is provided that the numerator becomes only a constant. But in this case, our numerator is not a constant. So we need to further simplify the numerator and break it down into simpler cases such that one of the root, we can make a root equal to the denominator in one case, and the other one could then be a constant number to make use of this. So in order to make the root similar to the denominator, let's simplify that a little bit. If we multiply the 9 over 40 by that, it will be 9 over 10s plus 9 over 40. And if we want to get to s plus 7 over 40, then let's take 9 over 10, and s plus is going to be 9 over 40 is going to be divided by 9 over 10, which in this case is going to be only s plus 1 over 4. Now, s plus 1 over 4 is different than s plus 7 over 40, so we can simply write plus 7 over 40, the minus 7 over 40. And in this case, s plus 7 over 40, these two can cancel out the denominator, and we just need to consider what would be this constant. This constant of 1 over 4, or 10 over 40 minus 7 over 40 would be 3 over 40. So it would be 3 over 40 as a constant plus s plus 7 over 40. So these would be numerators, and the denominator would be 40 times s plus 7 divided by 40 squared. So you can see that how numerator can be split into a single term of s and also a constant value. And you can break down this complicated function into simpler fractions. One is this fraction, which is a constant number divided by this squared root, as well as this first order function divided by the second order. So let's do that in the next slide. So we can have two different transfer functions of s1 plus s2, which in this case s1 then becomes 3 over 40 divided by 40 times s plus 7 over 40 squared. And further simplification of that would be 3 divided by 1600ths divided by s plus 7 over 40 squared. And we know that this can turn into 3 divided by 1600ths t e to the power of minus a, which in this case a becomes 7 over 40 t. So that is the time domain equivalent of S1. However, S2 is simply s plus 7 over 40 divided by 40 times s plus 7 over 40. And if you simplify that, one of the powers in the numerator gets cancelled. So we are left with only one term of 1 over 40 times s plus 7 over 40. And we know that into time domain, it would be simply 1 over 40 e to the power of minus 7 over 40 t. So S1 and S2 in time domain are going to be S1 time domain plus S2 time domain. Essentially, it's going to be 3 divided by 1600ths t e to the minus 7 over 40 t plus 1 over 40 e to the minus 7 over 40 t. So I'm going to highlight them to have a better connection of S1 as well as S2, which are given here. So that's how we could convert a complicated function into a time domain with breaking down into simpler pieces. So here is the exercise that I have designed. You can easily solve this with respect to the material you just covered. Uh, the differential equation given here is asked to be turned into a time domain at the end. But then the easier solution is that first convert them into a Laplace transform and into a frequency domain, and then solve in the frequency domain, then convert them back into the time domain. So hopefully you like this video, and please subscribe to the channel if you want to watch more videos like this. Have a good one.